Uh, so in this, from this topic, a subsection section of unknown standard deviation, when we don't know the individual standard deviation of those variables that we want to estimate, we have seen we estimated from the sample. We use the sample standard deviation in place of the sigma. And we have seen large samples from any distribution. When we have large sample from any distribution, because when we are estimating x bar or difference between, if you're estimating means or difference between means, they are still asymptotic. They're normal because of the central limit theorem, and we can use, when we have large samples, the sample standard deviation becomes a good estimate of sigma, and we can still use the same techniques we have earlier. And if we have small samples, so and sample size from and samples of any size from a normal distribution, we have our individual variables may be normally distributed individual, if we know that they are normally distributed individual variables. When they are large, it doesn't matter. But when they are small, they are still going to be normally distributed. But small samples with unknown standard deviation, that's the case where we're going to be using the t distribution, students t distribution. If we have a small sample of non-normal distribution, we are not going to consider that in this course at all. There are some techniques that are called bootstrapping, for example, in chapter 10. We are not going to cover that section of chapter 10. We're just going to cover first section of chapter 10, which we are going to see just chi-square tests to test for a family of distribution. So we are not going to be discussing these bootstrapping methods, but there are techniques that exist for small non-normal samples. So now we have seen large samples where we just simply replace the standard error with the sample by using the sample standard deviation. And when we estimate proportions, again, we use the sample standard, sample variance, again, to replace, to find population variance. And so here, what we do is, for this, since we have also seen how we use the maximum variance value, individual variance value of 0.25 when we are estimating proportions with a fixed precision. If you want to fix the margin, which is our precision, we can actually find the number of samples, the size of samples that we want to collect by assuming the worst variance. So we have covered these three things in the first hour. Now we're going to talk about small samples, and they're normal. We have to be given that they are normally distributed. Those individual variables are normally distributed. We have a small set of samples, a small size sample, and we don't know the standard deviation of the individual variables. If we have a small sample, but we know the standard deviation, then it's not students t, okay? If sigma is given to us in the question for small samples, we can still use the z distribution, because in that case, as the book states, this denominator will be the standard error, which is computed by linearity of expectation from the given standard deviation. So this is not going to, denominator is not going to be a random variable when we know the standard deviation of the population. But when we don't know it, it becomes an estimate of standard error. Then this is when we use students t distribution, okay? The only case students t is used is we have a small sample, individual elements are normally distributed, and we don't know the standard deviation. That is not given to us. So students t distribution was first proposed by William Gosset. So the student, actually, his pseudonym that he used when he published papers. I think he was a student of Pearson, if I'm not mistaken. So Pearson is also a very well-known statistician. Let's take a look at, let's verify this. Statistician, let's go to Wikipedia. Biography, so he went to, laboratory of Carl Pearson. So Gossett and Pearson had a good relationship. So student, so also known as student, as you can see, student is his pseudonym. Yeah, this T distribution, he also has other achievements. So yeah, he was a student of, well, he worked with Pearson, who is also a very important statistician. Now, so this is a bit history, and he found this student's T distribution while he was working for the Irish brewery Guinness, uh, and he described a T distribution for the quality control problems in brewing. So even in the late 19th century or early 20th century, they were trying to standardize the production of beer in quality, and in order to have constant measured quality of what is produced, so they were looking at different, they were taking different measurements for that brewed beer probably, and they didn't know their production devices, they didn't know their error rates beforehand. So the standard deviation was unknown. And the samples they collected probably in their quality department, they were small size. So he has figured out that the normal distribution cannot be a very good confidence interval estimate for this. So theoretically, so he did the mathematics of this actually. So this ratio of two random variables cannot be considered as a normal distribution. So he came up with student's T distribution. It has another parameter. The student's T distribution has also a parameter which is called degrees of freedom, which is sample size minus one. Because the standard error here, when we're computing it, the standard error, the mean of these n variables, when you consider the mean, it's actually coming from all the others. But if you just remove one variable out of those, since mean is already known, taking one variable out, actually the degrees of freedom in a sample with a known mean is n minus one, because you cannot make the last variable freely you cannot set it to any value freely, because changing its value is going to change the mean. Therefore, the degrees of freedom we have here in our sample is n minus 1. So simply, you may think that whatever your sample size is and your confidence level, so we are going to be looking at a different table, T alpha over 2. And if your sample size is n, you're going to be looking at not T alpha is going to be T alpha over 2 is going to be different for different values of sample size. So based on your sample size, you're going to be looking at a different part in the table. We didn't do that for the Z table, right? Z has only one parameter, which is alpha over 2. For example, Z 0.025 is 196. That's fixed regardless of your sample size. Here, the t value also changes. So this t value that we are going to be using here is going to change by sample size. We are going to use sample size minus 1 as our degrees of freedom. If we go take a look at that table, it's in appendix A5. This is A2, A4, and A5. So this is a table of students' t distribution. You can also again use Octave Online or MATLAB to find those t values. But here, this 0.025 was our z value for confidence level 9.5, right? It was 1.96. You see this 1.96 here? When degrees of freedom is infinity, for infinite degrees of freedom, the t distribution becomes the normal distribution. So as the sample size gets larger, the t distribution, it becomes the same as standard normal standard normal distribution. So this 1.96 is what we have when we have very large sample. Now, if you have, for example, 200 samples, you don't go, when you're building your confidence interval, your margin, as you can see, increases a little bit. So because since you don't know the standard deviation, when you're building your confidence intervals with the same confidence, since your precision decreases, which means that your margin increases. So this is seen by degrees of freedom here. For example, if you're just having 26 samples, you have to, with the same confidence level as we did before, 95% confidence, whatever what our standard error was, remember we were going 1.96 standard error to the left and to the right of that estimated value. Here, if your sample size is 26, instead of going 196 standard errors to the left and to the right, you go 2.05 standard errors to the left and to the right. As you can see, this may be not that much, maybe negligible depending on what your standard error is. It's only from 1.96, it's only this much an increase. But as your sample size gets smaller, the difference gets larger. For example, with only 10 samples, you have to go 2.22 standard errors to the left and to the right when you're building your interval. This table shows, this is the degree of freedom we see on the left-hand side. As the degree of freedom gets smaller, which means your sample size is getting smaller, with, for example, 12 samples, sorry, when I said this was, I said 10 samples, right? Actually, this 10, degree of freedom 10 corresponds to a sample size of 11, okay? Because you're doing a confidence test, confidence interval by using a small sample, n minus 1, where n is our sample size, is the degree of freedom of this t distribution. So this one, the row corresponding to 10 corresponds to a sample size of 11. So you can also see that z versus t distribution gets like this. As you can see, it has more a tail. So this is the t distribution, and this is standard normal distribution. This is a, depending on what the degree of freedom is, t distribution has heavier tails and its peak is lower, so it means that it's fatter. If you want to, again, put 95% of the population inside an interval, you have to increase your interval. And this is t distribution with a different, so n close to 30. As I said, this 30 is like a rule of thumb for large and small. So when n is close to 30, this is how t distribution and z distribution look like. And n very smaller than 30, it looks like this. All right, let's get back to chapter 9. So what we're going to do is, so this is how we're going to build the confidence interval. We are going to look at that table. Again, we are going to be using sample standard deviation to estimate population standard deviation. And let's take a look at this example 119. Here, unauthorized use of a computer account. If an unauthorized person accesses a computer account with the correct username and password, can this intrusion be detected? Recently, a number of methods have been proposed to detect such unauthorized use. The time between keystrokes, the time a key is pressed, the frequency of various keywords are measured and compared with those of the account owner. If there are significant differences, an intruder is detected. Okay, so here are for some typical particular user. These are the keystrokes that the user himself or herself have recorded when he or she was entering their password. So these are the in seconds time between two key presses. Now, as a first step in detecting intrusion, let's construct a 99% confidence interval for the mean time between keystrokes, assuming normal distribution of these times. So this is really important. In order to be able to use the t distribution, we should first assume that these individual, the time between two keystrokes is something that is normally distributed. We make this big assumption. This has to be given in the question, to us in the question. Then, since these are the users' things, what we need to do is let's build a confidence interval. And if we get something outside this interval, we're going to maybe assume that it's an intruder. Okay, so this confidence interval will be like a model of the user. You're going to model the user's keystroke patterns or the time between the user's keystrokes when he or she is entering her password. And then if we get something outside that interval, we are going to maybe just classify it as an intruder. So here the sample size is 18. We have 18 samples. The X bar, the average is 0.29 seconds. And the sample standard deviation is 0.074. So the sample standard deviation is the standard deviation of the individual items, data points. The critical value of t distribution with, we have 18, the sample size is 18, n minus 1 is 17 degrees of freedom. For alpha over 2, alpha here is 0.01. Divide that by 2, you get 0.005. If you take a look at with 18 degrees of freedom, the value of 0.05, it gives you 2.89. This value you see here is most probably larger, and for sure, it's a value larger than the Z 0.005. Okay, Z0, the standard from the standard normal table, if you look at Z 0.005, it will be probably maybe 2.5 or even less than that. Oh, the function for t, I don't know the just like the normal distribution, it has to have a PDF value. Let's take a look at Wikipedia. T distribution, I'm sure it has this n, the degree of freedom in its function. Okay, T distribution, not images. So it's this. So it's actually, this is the T statistic, how we compute that. It's not this PDF. Let's call it T distribution PDF. Students T distribution PDF should be here. So this is the PDF. So the function you're looking for is this one. So it uses the gamma function. We know actually this gamma function is like n minus 1 factorial. So this is v plus 1 divided by 2 factorial. If it's a non, so this gamma function is the same thing we use in our gamma PDF. Divided by degree of freedom. So this V here is the degree of freedom. So it has two parameters, degree of freedom. So degree of freedom is one parameter. And actually, yeah, that's the only parameter because this is the standard T distribution. The mu and sigma, which was 0 and 1 and standard normal, it's the same. The mean is 0 for V greater than 1. Its variance is this. So it has an interesting variance. Its variance is V divided by V minus 2. It's not 1. But what is it in for T distribution on Octave Online? I don't know. Let's search students T table, students T table, or T function Octave MATLAB. So this is TCDF. So TCDF is what you're looking for. Okay, so TCDF function will give you this. This is the degree of NU, I think is the degree of freedom. Okay, so this is the CDF. If you want to get the inverse CDF, so for example, if we plug in TCDF 17, not 17, sorry, 2.89, then 17 here, we'll probably going to get 0.9995. So let's go to Octave Online quickly. Let's try that out. So TCDF 2.89 8, what was that one in the book? 2.898. So it's going to give us 0.995. You're expecting that. So I forgot 0.898, 2.898, and 17. I will probably say it's load the statistics package. Yes. Package loads total power. Yeah, as you can see, it's exactly 0.9950. So this is the CDF, but when we're constructing those confidence intervals, we are looking for this 2.9. So we are looking at the inverse CDF. So we have to look at the inverse CDF, which is T-inv. So we will be looking at this one. Inverse cumulative distribution function. So and when we, for example, right here, T inverse 0.005. So this is our confidence level. 17 is going to give negative value, minus 2.89. So this is minus 2.89 is the cumulative distribution where 0.005 of the population is to the left. So this becomes our, we use this one's positive value as our standard deviation. We need to go this much standard deviations away from the mean to the left and to the right. Okay, so this is how we can use this directly to solve questions related to t-distributions. But yeah, thanks for asking that question. So I also get to know that in MATLAB. So this is the first time I used it in MATLAB as well. All right, so if we do it in this example, 289, yeah, if we, for example, do the same thing for Z, it was probably a smaller number. I told you, let's, is it the, if I do it like this, is it Z inverse or norm CDF, norm? Okay, how norm in, yeah, that's the normal inverse 0.05. Yeah, as you can see, it's 2.57. So instead of going to, if we knew the population standard deviation, we would be going 2.6, if you round it to one digit, 2.6 standard deviations away from the center. Now we are going 2.9. So it's therefore, as you can see, we know less, we don't know the standard deviation. The cost of that to us is an increased margin. We have to increase our confidence interval. And when we do that, it becomes between 0.24 and 0.34. So this is the user model. You can consider this interval as a way of user model. This is our model for the user. The user's keystroke intervals are between this and that. And we are 99% confident about this. So if, for example, somebody tells us that I have a password entry which took 0.37 seconds between keystrokes. That may be an intrusion because it's not inside this interval. But 0.37 is also too close to this. Or, I mean, if it was 0.6, you would be more confident that it's going to be an intrusion, right? 0.37, you can still say that you're 99% confident that it's an intrusion, but still, maybe something close to call. We are going to see in hypothesis testing, we are going to be doing exactly that actually. We are going to make some measurement, a sample, and we are going to have, assume some normal case. We are going to compare a single a sample against what we expect as normal. This is what we're going to see in hypothesis testing. So yeah, the density of students t-distribution is again a bell-shaped curve. Is symmetric. Its T alpha is always greater than Z alpha, as we have seen here. 2.89 is larger than 2.59. So it was a good way to compare those values as well. Oops, I need to go here. And degrees of parameter describes this V, the degrees of parameters is the number of samples minus one. But if the degrees the degrees of freedom that we're going to be here is that when we're using t-test for the difference between two population means. For example, if we have two population, we are going to see two cases. First, there are two cases where we assume they have equal variance. We don't know their variance. In both cases, we don't know their variance, but assuming equal variance is a big assumption. If we don't make this assumption, if the two populations may have different population variances, the degree of freedom, that's a very difficult thing, and the degree of freedom is actually approximated by something. So this is here comparison with two populations with unknown variances. So this 935, this is the last thing we're going to be discussing today before we finish this section 9.3. Here, there are two cases as discussed here. Assuming equal variances, two populations, although we don't know we don't know what they are, but if we assume they have equal variances, we can just use this with a standard t-test where we use the pooled sample variance. We put together the standard sample, we just put everything together as if it's a single population because they have the same variance, and we compute the pooled sample variance by using that. And the denominator here becomes our degree of freedom when we're going to make the t-test. So our degrees of freedom will be n times m, the summation of the total sample size minus 2. Okay, because this Sx and Sy, they are again computed, the sample variances are computed individually by looking at n minus 1 and m minus 1 data points. That's the degree of freedom. So the total degree of freedom is n times m, not times, m plus m minus 2 will be our degree of freedom. So in short, so this box here shows how you're going to find the confidence interval between two means if you don't know their standard deviations. Population standard deviations are unknown. You first compute the pooled standard deviation as in this formula. So this is the pooled variance. As you can see, everything in this is going to be computed from our sample, collected sample. So xi's, yi's are sample data points, x bar, y bar is our sample average. So this formula, you can just write a simple for loop to compute this or this pooled variance directly. Okay, and this T alpha over 2 is going to be the critical value from the T distribution with n plus m minus 2 degrees of freedom. So for equal variance, we conduct a student's t-test, and we use n plus m minus 2 degrees of freedom. Now, the case 2 here is a difficult case, okay? The first case was there exists an exact and simple solution based on t-distribution is what I just showed you. The other case, if we don't assume equal variances, it becomes a difficult problem, it turns out. It's called the Behrens-Fisher problem, where no exact solution exists. So there is no exact solution for that problem, and only approximations are available. And the approximation that we see here, even the approximation itself, you're going to see is complicated. It's a complicated formula. So this one is an example, 9.20. You may take a look at it later at home to see how we use the pooled sample variance. But the example is very simple. Just first compute the pooled sample variance and go that many standard deviations away by finding it in the table. Okay, 2.0.48 is the degrees of freedom. By using a certain degrees of freedom in the T table, we find this out, and we go, this is our difference, and this right hand side here is our margin. And there's a remark here why the degrees of freedom is m plus m minus 2. I'm going to skip that one. And the last thing we're going to discuss today is this unequal variances case. And here, look at this. Let me just want to show you this. Look at this V. This is the degree of freedom that we are going to use. Compare this with m plus m minus 2, which is really simple formula, right? Sum of population sizes minus 2 was your degree of freedom. But this Satterthwaite weight approximation is a very complicated formula that it shows the degree of freedom that you should use in that T distribution. So we are not going to go into details of this, and you should memorize this. If we ask something about this in the exam, this is going to be available to you directly. So you're going to apply this by referring to this 9.12. But as you can see, this part is exactly the same we did before. We instead of using pool standard deviation, we actually use individual standard deviations and add them up like this. And here, the degree of freedom, the degrees of freedom that you're going to find, this V is given by this complicated formula, which was which is an approximate solution proposed in 1940s by Franklin Satterthwaite, who worked for the General Electric company at that time. Okay, so this is as I said, this is a complicated case, which we are not going to go into too much detail. So here, even in the example, you see how. I mean, it's complicated, but everything here is actually known. If you look at this equation, after you compute your sample standard, sample variance for both samples, after you compute those, you just plug that in those formulas where we also have the sample size. You plug that in, and it turns out V is 25.4. It may not be an integer. Okay, so we round it to the closest integer in the table. They use 25 with 25 degrees of freedom with this confidence level, 0.05 confidence level. We get a t value of 2.06, and that t.06 plus the standard error away from the center. So this is how we do that. Okay, so let's see whether I have anything on the slides. Otherwise, we're going to finish early today. I will just give a short introduction to hypothesis testing. But yeah, this is our degree of freedom. This is when equal variances, we have this. SP is the pool standard deviation. When unequal variances, we use this, and I don't even have the degree of freedom formula. So this is actually, this slide contains missing information. Okay, you're going to look at the T alpha over 2, but what is your degree of freedom? So this T distribution, you should also indicate what your degrees of freedom is. In this case, degrees of freedom is m plus m minus 2. Again, it's not indicated here, and so this slide contains some missing information. What is our degree of freedom? Degrees of freedom, m plus m minus 2 in this case. And for unequal variances, it's this complicated formula that we have seen in the book. All right, so this concludes section 9.3. The only remaining thing from chapter 9 is hypothesis testing. You're not going to cover 9.5 from this chapter. You're going to finish our chapter 9 discussion on chapter 9 by finishing this section, this section. So hypothesis testing is when we are going to, it's very similar to what we have done in confidence interval actually, but this time we are going to be testing against some normal thing. And H0, we are going to construct a hypothesis. For example, we'll be asking, let me just finish actually by giving an example by using this example we had here. Imagine this is, so we build a confidence interval for a user model for, so this was the sample that we have collected, right? Imagine this time we collect a different sample. In this case, the so this was the real user, and it maybe averages between different things. Now imagine we don't know whether it belongs to that user or not, but we collect some interval times between keystrokes for somebody else. Okay, and we want to determine whether it's this user or another user. Now, we are going to construct a hypothesis test for that. For example, our hypothesis, we may want to figure out whether it's an intruder or not. The null hypothesis is that the null hypothesis is something, an hypothesis that is that determines the normal case. Okay, it means that the this is not the intruder. Okay, so normally we are going to expect the user himself or herself to enter that keyword, the password. But in observing an intruder is an unlikely case. So that will be our alternative hypothesis. And our hypothesis in this case will be something like that. The normality, that this is our user, is going to be indicated by with an equality. For example, we'll be saying the mean is equal to, for example, we're going to say the mean value is equal to 0.29, right? Yeah, 0.29. So this is our hypothesis. And we are going to collect the sample in this case, in which it has a certain, and this is our normal case. The alternative in the other case, okay, the alternative hypothesis will be mu is not equal to this thing. So we are going to collect a different sample, and this by using our sample, which may be collected from intruder or not, we are going to try to determine whether the sample we collected belongs to this null distribution, it's a normal case, or it's the alternative. It's somebody else with a different mean. It's not the same person with 0.29. And we are going to be, it's very similar to the discussion on confidence interval actually. When we build a confidence interval around this 0.9, we, with 99% confidence, we actually, around this 0.29, we build a confidence interval where the actual mean is in this interval with 0.99 probability, or I mean this interval contains the actual mean with 0.99 probability. Now if we collect a different sample and it turns out to be the keystroke interval turns out to be here or here, if it's outside this interval, we are going to say that it's something not normal. So this is, we are going to reject the null hypothesis in this case and say that, okay, there's something not common, not normal going on here, and that person may be the intruder. So hypothesis testing is going to be similar to those confidence intervals we have built, but yeah, we're going to talk about that in detail next week. Okay, so I'm going to stop here. The only thing from chapter 9 is this hypothesis testing 9.4, and we're going to talk about that starting on Tuesday. And we'll finish it by next week, and we're going to start chapter 10 the following week. All right, that's it. And by the way, your third assignment is going to be about another written assignment on chapter 9, and it's going to be announced after we finish chapter 9. Okay, it's going to be announced not this Friday, the following Friday, probably, when we finish chapter 9, and it's going to be a written assignment on chapter 9. Okay, if you don't have any questions, I'm going to finish recording now.